Okay, we're going to continue on here, chapter 10. So chapter 10, which should be the last chapter on the upcoming exam, which I think is next week. So chapter 10 was about energy. We started talking a little bit about energy and some different types of energy there to sort of finish up last time. And remember that, there's really kind of two forms of energy, as we'll talk more about here today as well, that we talk about, are processes that we talk about, and those are really exothermic or endothermic processes. And one is basically will release energy, which is exothermic, and one will absorb energy. And sort of what we talked about last time is we think about energy always sort of as a nice perfect transfer between really kind of two things. And one thing is a system, and pretty much everything outside of that is the surroundings. So again, if the system loses a certain amount of energy, the surroundings will pick up that exact same amount of energy, and really vice versa. If the surroundings actually lose a certain amount of energy, the system will pick up that amount of energy. It is just different depending on sort of which direction you're talking about. So if the system loses a certain amount of energy, it's going to be exothermic for the system. If the surroundings picks up that energy, it will be endothermic, but the amount of energy will be the same. So the new sort of numerical value, if you want to think about it that way, will be the same for both of them. The sign, though, will be different, as we talked about, and we'll talk about again. Typically speaking, negative values for energy is exothermic, positive values for energy is endothermic. So you'll have the same sort of numerical value, just one will be positive, one will be negative, depending on sort of the direction of the flow of energy from one place to the next. That's sort of the law of conservation of energy, which is sometimes referred to as the first law of thermodynamics. We basically have a conservation of energy. We don't create it nor destroy it, but again, it can be sort of transformed from one version to the next. All right, so we're going to kind of pick up there sort of where we left off. I think it was on this slide, I think. So when we talk about thermodynamics, we talk a little bit about here. In 1A, you'll talk about thermodynamics, a little bit more about energy. And in 1B, you'll talk about the whole chapter about thermodynamics. But thermodynamics oftentimes deals with a couple of things in addition to energy. A lot of times when we look at thermodynamics, the sort of question that we're trying to sort of determine is whether or not a reaction will occur spontaneously. And sometimes people have a misunderstanding about the sort of term spontaneously. We can have a reaction that's spontaneous, and really all that means is under those conditions, we would expect the reaction to occur and happen. Sometimes people think about it, the word spontaneous, and they automatically assume sort of how fast the reaction would happen. Like if you snap your fingers, it's spontaneous, it's going to happen really fast. But really, spontaneity and sort of thermodynamics doesn't really deal with the idea of how fast or slow a reaction takes place. That's actually the area of study, which is kinetics, and kinetics deals with how fast or slow a reaction takes place. But thermodynamics and the other part of thermodynamics really deals with the idea of whether or not a reaction is sort of spontaneous or not. And sort of the energy component to that is a lot what we'll focus on in this chapter, not so much was this reaction spontaneous or not, but more about the energy. And one thing about energy is energy are considered state functions, and state functions are really properties where it doesn't really matter how you got there. Really, the only two important things is basically where you started and where you ended. And that's what we see here, things like energy, pressure, volume, and temperature. On this graph here, our picture, we have two hikers. They both started at the same point. The guy in the blue took the more direct route up the mountain. The guy in the red took the more scenic route around the mountain. But they're now both standing pretty much in the exact same location, which means in terms of their potential energy, they do have the same potential energy because they basically started and ended in the same location. And a lot of things are like that in chemistry: change in energy, which is delta E, change in internal energy, change in pressure, change in volume, change in temperature. That's why a lot of times what we calculate is kind of final minus initial states, and that's sort of where you started and where you ended up, basically, is how we calculate a lot of these sort of values. In terms of things like, as we'll talk about a little bit later on, something known as delta H, which is the enthalpy, which is the heat of a reaction. We oftentimes, in these type of calculations, and also a lot of thermodynamic calculations, we kind of take the difference between the products and the reactants values. And if you think about a chemical reaction, basically we have our reactants, which is our starting material, and we go to products, which is our stuff that's formed. So products are usually like the end position, and obviously reactants are like the starting position. So a lot of thermodynamic sort of calculations involve basically taking the difference between like where you end with your products versus where you started with your reactants. And in terms of energy, that is also what we kind of look at, is kind of products minus reactants, kind of our final state and our initial state. Other things that you'll learn as you go through chemistry is not all reactions take place in a one-step fashion. It's not all just from reactions directly to products. Sometimes reactions take place in multiple individual steps along the way. So, you know, for example, if you had something like A plus B goes to E plus F, we sometimes look at the overall reaction and assume, okay, it's like a one-step sort of process. But this reaction could occur like A plus B goes to C plus D, then C plus D makes some E plus F. And these are separate sort of reactions that occur. And if we add reactions together, which you can do, and whenever you add a reaction together, anything that's on opposite sides of the arrow that are the same will essentially cancel out. There's kind of like subtracting it from the other side. Kind of think like the arrow is an equal sign. So in this case, the C and the C would cancel, the D and the D would cancel, and then everything on the left-hand side stays on the left-hand side. Everything on the right-hand side stays on the right-hand side, and this would be our overall reaction. But sometimes we just look at overall reactions and sometimes think okay, it's just like a one-step sort of process, but lots of reactions actually occur in multiple sort of little reactions until they get to the end. Sometimes referred to as the reaction mechanism, which when you learn about kinetics, not in this class, but in later class, you will learn about that as well. Any questions on that there? All right, so we talked, I think, a little bit about some of these units here, but let's just make sure. Energy, the SI unit is Newton meters, although in chemistry we don't use Newton meters all that much. As we mentioned before, a joule is definitely a unit. And by the way, none of these are negative, just from PowerPoint, so don't make me think it's negative. But this relationship is a very helpful relationship, although we may not see it very much here. As you continue on in chemistry, you will see this relationship at a number of different places. 1 joule is equal to 1 kilogram meter squared second squared. So that's really something that you should know. Definitely 1,000 joules is 1 kilojoule is something you should know, as that is used a lot. Another unit of energy that's important is calories. As we might have talked about it before, our calories with a little c is basically the amount of energy that's required to raise 1 gram of water by 1 degree Celsius. And the relationship between actually calories and kilocalories, which is another, again, very common unit, and that again is something that you should know. 1,000 calories is a kilocalorie. This conversion here to go from calories to joules, 1 calorie is 4.184 joules. So that again is also something that they expect you to know as you continue on through. And that's a conversion you'll use a lot. I will say, as I mentioned before, probably joules and kilojoules is mostly the units that you will probably see the most in terms of energy. I would say calories and kilocalories squeeze in there a little bit, but not all that much. but definitely joules and kilojoules for sure. But you do need to know how to go between those two, calories and joules. Any questions on those things there? As we might have talked about last time as well, there is another calorie, which is a nutritional calorie, and that again has a capital C, and that is equal to 1,000 of the lowercase c's, and that's the same as 1 kilocalorie. So this is sometimes also referred to as a nutritional calorie, which is obviously what we think about when we deal with food and energy burnt from food or exercising and stuff like that. That is sort of what we look at. Now, thermal energy, as we touched upon, is the energy associated with the random motion of molecules. And it is related to the more molecules that you have, the more thermal energy you're going to have in that particular case. Now, as I mentioned, we have a difference between temperature and thermal energy. Again, if we have a cup of coffee that's 70 degrees versus a bathtub of water that's 40 degrees Celsius, because the bathtub does contain a lot more molecules, there's going to be a lot more thermal energy. Although its temperature may be lower than the cup of coffee. And that is because, again, temperature is a measure of the heat in a particular situation. And in a cup of coffee, we don't have as many, say, water molecules in there. So it doesn't take as much energy to raise the temperature of that volume of water, if you want to think about it that way. Rather, if you're trying to heat up the entire bathtub, again, it's going to take a lot more energy to change that temperature along the way. And again, water has a fairly high specific heat capacity at 4.184 joules per gram per degree Celsius. So it takes a lot more energy to raise the temperature just a little bit of a bigger volume of water than it does, obviously, in a much smaller volume, right, of water. So, but in terms of thermal energy, although the bathtub may have a lower temperature, it does have a greater thermal energy because obviously it contains a lot more molecules of water. Any questions on that there? So heat is the difference and can be defined as the flow of energy due to some energy difference. And heat flows from cold to hot, hot to cold. Which way does it go? Heat flows from hot to cold. Yeah. So something that's hotter will release the energy, right, to something that's colder. The guy that's colder will pick up the energy and it will start to raise its temperature. And what we would see, obviously, with the thing that is hotter, it will start to lower its temperature as it starts to release that energy, right? So if you took a piece of hot metal and you dropped it into some cold water, we would see the metal's temperature come down, right? And we would see the water's temperature come up as it gains all that energy from the hot metal that was put in there. So as we talked about, exothermic, again, is any process where heat and energy is released. Like when you light a Bunsen burner or anything like that, you could put your hand near the flame and you could feel the heat coming off. It's releasing heat and energy to the surroundings. Endothermic process, again, is any process where heat and energy is being supplied to the system as absorbing energy. So again, you know, if you took an ice cube out, although you may not do anything to the ice cube, it's going to pick up all the heat and energy from the air, because the air is a hotter temperature, right, than the ice cube, right? So we're going to flow from hot to cold. So the air is going to send the energy into your ice cube. It's going to start to melt, right, as it picks up all that energy. So for the surrounding air there, it is actually going to be exothermic as it releases it. For the ice cube, is going to be endothermic, right, as the system sort of picking up that energy that's coming around. And that's also opposite, right? When you take liquid water, right, and you put it in the freezer and you want to make ice cubes, the freezer is colder, right, than the water that you just put in there. So the heat's going to transfer from the hotter water to the outside surrounding temperature of the freezer. And that's going to cause the water to lose energy, right? And that's how it goes back into the solid phase. Any questions on that? And obviously in that example, it would be exothermic for the liquid water in the freezer, and obviously endothermic for the freezer as it picks up all that energy. So that brings us to these guys here, and these are what are sometimes referred to as energy diagrams. And these are two different diagrams. One's an exothermic process and one's an endothermic process. And once again, just like we were just talking about, we have in a reaction our reactants that go to our products. So once again, it's chapter 10, so they figure you probably did the chemical reactions chapter and equations. But as we go from reactants to products, this is the process of a reaction or a chemical change occurring. And remember that when we have a chemical reaction, the only thing that's happening is we are basically breaking all the bonds on the reactant side, and we're reassembling all the bonds sort of on the product side to make our new compounds. So we're basically breaking bonds and we're making bonds on this side. And making and breaking bonds only involve electrons, and that's why we have conservation of the elements. We don't play with anything that involves protons or anything like that. So we do have this conservation of elements that occur. They just, again, rearrange into something new on the product side. So if we started with 4 carbons on the left, we'll end up with 4 carbons on the right of the reaction, again, just maybe in a different location. So when we look at an energy diagram, this is basically for this one here, this is our reactants, this is our products. And when we look at the difference here between where the reactants start and where the products end in terms of energy, the products are lower in energy than the reactants, which means the only way for those reactants to get down there is energy needs to be released, if you want to think about it that way. And that allows those reactants to get down to the products here in this particular case. The actual difference between where the energy of the reactants and the energy of the products here is what is referred to as delta H, again, are the change in enthalpy. And that is a fancy word for basically the heat of the reaction. How much heat's either absorbed or given off by this reaction. And as I mentioned before, and as we will see, one way to calculate the delta H of a reaction is to take the delta H of the products minus the delta H of the reactants, which again is our final minus initial constant sort of values. Now, if we look at this diagram here, we see our products are actually, again, lower in energy than our reactants, which means if we actually had a value for our products, should it be a higher or lower number than the reactants in terms of energy? Because the products are actually lower in energy than our reactants. If we actually had a number, it would actually be a smaller number than our reactants, right? If you just think about it sort of magnitude wise. So if this is our energy of our reactants, our products, that is much smaller than the energy of our reactants. So actually we would have a smaller number minus a larger number. And that means when you take a smaller number minus a larger number, you end up with what type of number, positive or negative? You end up with a negative number. So that's why we were talking about earlier that exothermic reactions in terms of energy and delta H, which is a change in enthalpy, is a very common way in chemistry that sort of exothermic and endothermic and energy is displayed to you. They'll give you a reaction and they'll go, the delta H value is this number, whatever it may be. And if you see that number is a negative number, you know it's an exothermic sort of situation, just like this. Also, if you look at this energy diagram like we see here, anytime you see an energy diagram like the one on the left, where the reactants are higher in energy than the products, it is always a exothermic reaction that's taking place. Any questions on that? And that is a little bit different than what we see on the endothermic side. If we look at the endothermic side, this is where our reactants are starting. This is where our products are at. And in this case, our products are actually higher in energy than our reactants. So if you want to think about it, in order for our reactants to get up there to our products, energy needs to be put in to do that. So to kind of get them up there in that energy scale, we got to actually, energy needs to go in or be absorbed. And we could do the same sort of calculation just by looking at it without actual numbers. But again, if we took the difference between where the reactants are in energy and our products, this would be our delta H of the reaction in this case. And for this guy, the delta H, again, if we took the delta H of our products minus the delta H of our reactants, once again, our sort of final minus initial state. In this case, we can see our reactants are actually lower in energy than where our products are in terms of energy. So that means that our products actually will be a larger value minus a smaller value. And that's going to end me with a positive number in this case, right? If you take a larger value minus a smaller value, you'll end up with a positive number. And that's why we associate positive values for delta H or energy to be a endothermic process that requires energy to be put in. Any questions on the differences there? Now, while we look at this energy diagram, there is also a couple of other things that's really important. And I'll continue the scribble maybe. Let's see here. So we'll go with let me go with this one. Now, there's actually this sort of hill. So as the reaction is progressing, the reactant's got to climb this hill of energy basically as it tries to get to the other side. And this hill of energy has a special name. It is what is known as the activation energy. And the activation energy is sometimes abbreviated as E of A, is the abbreviation for activation energy. Activation energy is the minimum amount of energy needed for a reaction to take place. So the activation energy is that minimum amount of energy that's required for a reaction to take place. In order for a reaction to take place, in order to have products that are actually being formed, you need basically two things to happen. You need basically a collision to occur. They got to actually hit each other, and they actually have to hit each other sort of in the right locations. So they have to hit each other in the active spots. They could collide as many times as they want. If they don't really hit each other in the right location, you'll never get products that are going to be formed. So sometimes people think all you need is, for them to kind of come together, but they actually need to come together in the correct location. And second to that is with the correct amount of energy, which is sort of like your activation energy. They have to actually hit each other in the right spot with the right minimum amount of energy in order for this reaction basically to take place and products to basically be formed. So you can have collisions that don't meet those sort of circumstances, and you will not get products to be formed. We also see the same sort of activation energy over here in our endothermic. So this hill, as we're climbing up, is our activation energy for our endothermic. All the way through here is our activation energy. Now, when we get to the very top of this sort of hill of energy, it is also sometimes referred to as the transition state. And the transition state will also usually have something there, sort of like an intermediate, sometimes referred to as the transition state complex or activated complex. So right here at the very top of the peak, you have this sort of, something going on up there. We'll just call it A, B together, sort of happening. And this is what is sometimes referred to as transition state complex or activated complex. And this is usually something at the very top of the hill there that has really partially broken bonds and bonds that are partially being made. So as it's sort of climbing up this hill, as it goes from reactants to products, really, and more so as it's climbing up this initial part of the hill, as it gets up there to the top, you're starting to break the initial bonds that are there, which is what needs to happen in a reaction. You need to break all the bonds that are there, and they're partially being broken. And then as it gets to the top, you're also starting to make some of the new bonds that are going to happen. So you have these things that are intermediates at the very top of the hill, which have partially broken bonds, partially made bonds. And when we're at the very peak of this hill, which is the peak of energy, are things in chemistry more happy when it is high in energy or lower energy? What's a better state for things? Yeah, low energy is where things are more stable. So it's really the point of almost anything that happens in chemistry is to bring the energy down of everybody, is sort of what is trying to happen in a lot of things that happen in chemistry. So when we look at this graph, this is really the peak of height in terms of energy. And that means that those transition state complexes, they're super unstable, right? Because they're very, very high in energy. They got partially made bonds, partially broken bonds. So usually very, very quickly, and it's oftentimes very hard to sort of isolate that transition state complex. Usually very quickly, they will kind of find themselves coming back down the other side to make products. So they really don't hang around very long at the very peak of energy there, where you got the partially made bonds, partially broken bonds. It's very quick and usually a very rapid sort of drop down into our product formation. Any questions on that there? So these are energy diagrams. You do need to be aware of them. And again, anytime you see reactants higher in energy than products on these diagrams should be exothermic, and vice versa there. When you see your reactants are lower in energy than your products, it should be an endothermic process. By the way, which one just from these graphs have the larger activation energy? Endothermic, which kind of makes sense since it needs kind of energy to put in there, right? To get enough people up and over the hill. The activation energy, we talked about the idea of sort of the rate of reaction. Thermodynamics doesn't deal with rates of reactions, but kinetics does. And when we look at something like the activation energy hill, it has a big effect on how fast or slow a reaction is, right? So if I have a bigger hill to climb to get to the other side, we probably would have a slower reaction, right, than if you had a smaller activation energy hill to climb to the other side, right? Just like if you were walking up a hill, you had a giant hill, it'd probably take you much longer to get up and over to the other side. If you had a much smaller hill, right, you could go up and over probably a lot quicker. So the activation energy is sort of that energy barrier that determines in terms of how fast or slow reaction takes place, how fast or slow the reaction takes place. So one way that we can overcome that is by the use of a catalyst. And a catalyst, for example, why we have this pictures here, actually, I'll draw one here. So if we have a normal reaction here, by the way, the one I just drew here is exothermic or endothermic. This is an endothermic reaction, right? Again, our products are higher in energy than our reactants. So one way that a sort of catalyst, for example, works, and a catalyst is a lot of times in reactions written up here on the arrow. It may be written as like an actual thing, like platinum or H plus if it's an acid. But what a catalyst is, it's not a reactant. It's not a product. And it actually does not get used up in the reaction. One of the ways a catalyst is there, or why a catalyst is there, is it typically will speed up the reaction. So a catalyst will typically speed up a reaction. And how does a catalyst speed up a reaction? It actually finds a alternative pathway for that reaction to take place. So for example, maybe you have gas molecules flying around, right? And for that reaction to take place, they got to go find each other. And maybe it will happen. Maybe it will be a spontaneous reaction, but it might take a very long time for those guys as they're flying around to try to come in contact with each other. So maybe you add a catalyst, like a metal to it or something like that, where the metal is kind of attracting everybody to a central location. And that's going to allow them to obviously come in contact a lot faster than they would if they were just kind of flying around sort of randomly about there. So sometimes we use things like metals, which, you know, although they're not in the actual reaction, but they do provide sort of a surface where everybody is attracted to, allows for everybody to come together a lot more efficiently than it would if they were just randomly sort of trying to find each other. Not to say they wouldn't happen if they were just randomly doing, but it would take a lot longer of a time for it to sort of happen. So ultimately, by finding this alternative pathway, what a catalyst does is it actually will affect the activation energy, which in this original drawing here would be here. By finding that alternative pathway, it's able to lower the activation energy. And by lowering the activation energy, what a catalyst will essentially do is it will allow a greater proportion of reactant molecules to now have enough energy to get up and over to the other side. So by lowering that hill that those reactants has to climb to get to the other side, it in turn will typically speed up a reaction. Not all catalysts actually speed up a reaction, but most of the time when people talk about a catalyst, that's usually what they're talking about, is speeding up a reaction. There's actually negative catalysts that will kind of slow down a reaction, but I would say 99 times out of 100, somebody's talking to you about a catalyst, they're probably talking to you about speeding up a reaction in most cases. Any questions on energy diagrams, difference between exothermic, endothermic, activation energy? Amy? All right. So here's just another sort of version of some of those energy diagrams, but here we have this reaction here. This is our reactants, that's our products. So once again, here we have our reactants higher in energy than our products. Again, and the only way for that to sort of happen is it has to give off energy to the surroundings, and that would be exothermic. In this case, we're taking mercury 2 oxide, which is our reactant, going to our product where we make some mercury and some oxygen. And in this case, we see the opposite. Our reactant is lower in energy than our product. So again, energy has to be put in from the surroundings to allow that to occur. Now, a couple other ways that we do think about energy and think about exothermic and endothermic. Obviously, we've talked about exothermic releasing energy and endothermic reaction absorbing energy. Sometimes you will see in the actual equation like an energy value written in, or you may just see generically heat written on one side of the arrow versus the other side of the arrow. So when we think about exothermic reactions, we think of it as the energy part, which is this guy right here. And again, it may just be written generically as heat on the product side. We think of heat and energy as a product in a exothermic reaction. So again, like it's being given off, like our products are being made. So in addition, we're also giving off that energy in that process. So it is very common sometimes that people will just generically, like I said, write heat on one side of the arrow or the other. So if you see heat written on the product side, our natural value, like it is in this example here, you know it's an exothermic reaction. And vice versa for our endothermic, where heat is absorbed, heat is considered a reactant. And it'll be on the left-hand side of the arrow. And again, may be an actual value, may actually just say heat written there. But again, if you see heat or an actual value of energy on the reactant side of the arrow, which would be the left-hand side, then you know it's an endothermic reaction overall. I will say, as I mentioned before, probably most common the way that you will see these things is just a reaction given or an equation, and the delta H value will be given to you. And again, if it's negative, as we talked about a second ago, it will be exothermic. And if the delta H value is positive, it will be endothermic. In terms of exothermic and endothermic, and you're given like an energy value or a delta H value, it doesn't really matter the number. The only thing that really matters is the sign. Is it positive or negative? And that's why as you calculate things that involve energy, you should leave the sign the way you find it. So if you end up with a positive value, you should leave it positive. Or if you have a negative value for energy, you should leave it negative, because that will tell the person what type of reaction you're dealing with, whether it's exothermic or endothermic. So sometimes in lower level classes, people are taught, don't worry about the sign of the energy, but it really is important, especially as you continue on in 1A and 1B, to always keep the sign that you get for energy sort of calculations as either being positive or negative, again, because it kind of tells you exothermic or endothermic. Any questions on that there? So here's an example of what we were talking about, some pictures from your book. Again, the flow of heat and energy will go from hot to cold. So in this case, if we have a couple of different temperatured water there in an isolated container, the hot water side there will transfer the energy over to the cold, and we will start to see, obviously, the cold side pick up some more energy, which will make those water molecules move a little bit faster. And we should see this represented in terms of temperature as our value, right? That we can see what's going on. And we will see that our hot temperature will cool down and our cold temperature will heat up. And if it's in a nice insulated container like that, they'll probably meet somewhere between the two temperatures when you take the average and add them together and divide by 2. So this brings up an important part about temperature. A lot of times we use temperature to determine what type of reaction is taking place or what is happening when something takes place. So when we think about temperature and we take our temperature reading with our really badly drawn thermometer there, and we take our initial temperature and then we take our final temperature at the end, and if our temperature increases, whatever we were measuring, would that thing be endothermic or exothermic? The temperature increases. In terms of whatever we have the thermometer in, is it gaining energy or losing energy? If the temperature goes up. If I light a fire on or something, will it get hotter or colder? Hotter, right? So that means that whatever I'm measuring, say it's a beaker of water, is actually becoming hotter, right? Which means it's gaining energy, which means it is absorbing energy, right? So it will be endothermic, right? If I had that in there. If I put my thermometer into my beaker of water and all of a sudden I see the temperature start to go down, right? And the temperature goes down the opposite way, right? So this would be absorbing water, right? Absorbing energy. We'll put it in something here. We'll put in some water. And if I take my thermometer there, right, and put it into some water, and I see the temperature starts to go down, right? That means that it is releasing the energy, right? The only way for that temperature to start to go down is it has to give off the energy, right? So it has less energy. The water molecules that are left, right, are slowing down and they're going to have less motion. Less motion means less energy, and the temperature decrease as you go through it, right? So we do look at a difference in temperature to help us know, what type of process. And it does the same thing when we do a change in temperature, right, of final minus initial. In the case of absorbing energy, if our temperature increased, this would be a larger number, right, minus a smaller number, which will give us actually a positive value, right? On the other case there, our final temperature minus our initial temperature, if our final temperature was lower, this would be a smaller number minus a larger number. That's going to give us a negative value. So it is actually the change, and we're going to see this in a calculation in just a second, or in this chapter. It's actually the temperature component and following the temperature change that actually helps us get either a negative or a positive value when we calculate something like specific heat, which we're going to calculate in this chapter. So that falling in temperature allows us to understand, whatever we're measuring, is it absorbing energy or where is it releasing energy? This is obviously based on where the thermometer is sticking in as to what we see. Any questions on that? All right, so speaking of enthalpy, which, as I mentioned before, is probably in chemistry your most common sort of energy calculation that you do. And most reactions that are carried out under constant pressure condition, we can use the delta H, or the change in enthalpy, to understand what is going on. And that's what the little delta symbol in front of the H means. That's delta H, and that means change in enthalpy. The little triangle thing is the delta symbol. And as I mentioned before, the way that we could calculate the delta H for a reaction is to take the delta H values for your product minus the delta H values from your reactants. Now, when we do this type of calculation and you're asked, for example, to calculate the delta H for this reaction, and all they give you is pretty much the equation, this is typically where we find these values are in tables. So we could typically find these values in tables. And it's usually like delta H of formation type of values. And it's important when you go to these tables that you look up and you find what you're looking for in the right state. What I mean by that is solid, liquid, gas, aqueous. So it's really important that whenever you go to a table, like I say, a delta H table, and later on when you go to 1B, delta S table, delta G table, all those kind of guys, that you do find what you are looking for, but you want to make sure it's in the right state. Is it solid? Is it liquid? Is it aqueous you're looking for? Because there will be different values depending on, you know, which state it's in. And it's very common, for example, people will always go look up water and they just grab the first water they see on the table, and it may not be the correct sort of state that water is in, and you'll have the wrong value. So it's really important to do that. Now, the other thing that's important when we do products minus reactants and we do these type of calculations is when we have a reaction, and let's say we went to a table and we found, you know, A is say 5 kilojoules, B is minus 6 kilojoules, and C is minus 25 kilojoules. Let's make up some numbers. So let's just say we went to a table and we found these values. We found them in the right state that they're in and everything like that. We would calculate the delta H of this reaction by taking our products minus our reactants. And what we want to do is go delta H of this reaction will be our product side. Now, the product here and the reactants, they have coefficients, and typically in a chemical equation, they have coefficients. And these coefficients represent what are referred to as the moles of each of these things. So that is the moles of each of these things, abbreviated MOL. Mole, MOLE is the whole thing. And this is also what's sometimes referred to as sort of stoichiometry of each of these things. There's sort of 2 moles of A in my example. It would be 1 mole B because there's nothing written there. So in chemistry, if there is no number, it's pretty much assumed to be 1. So for the B there, just assume that there's a 1 in front of it. For C, there's 3 in front of it, which means there's 3 moles. So typically these values that you find in these tables are actually what are sometimes referred to as kilojoules per mole. So when we take these values from these tables, we want to actually multiply by the coefficient we see in front of these things. So we were going to do this. We would start on our product side. We would take 3 times the value of C from the table, which would be 25 kilojoules per mole. And that's all of our products. We are then going to subtract it from all of our reactants. And on our reactant side here for A, there is 2. So we would take 2 times the value of A from the table. There is also another reactant here, which is B, which means we would add it to the other reactant. And again, you don't need to really put the 1, but it's basically 1 times the value we would see for B in this case. And if we did all this with my made up numbers, let's see how bad I did here. 3 times negative 25, it equals minus 2 times 5 plus negative 6. So it looks like I end up with, my calculator's right here, negative 79 kilojoules as my delta H for this. And this would be, again, the difference between our products and our reactants, where we ended and where we started. In this example, would this reaction be endothermic or exothermic? It would be exo. Number doesn't matter. It's actually the sign that we see here. So this would be one where overall energy is going to be released from this reaction as it takes place. Any questions on that? So when you do this type of calculation, you got to make sure you take into account those coefficients times the values that you find from the table. Any questions on that one there? All right, so I want to try one here with some real numbers. Why don't you give it a go? So calculate the delta H for the following reaction. Here's the Okay, let's take a look since we're getting to the end here. So once again, we're going to do our delta H of our reaction, our products minus our reactants. So on the product side, which is this side, we have 2, which is the coefficient, times the value of sodium hydroxide from the table, 470 kilojoules per mole. We then have 1 times the value of H2, which is 0, minus our reactant side. So we have 2 sodiums, which from the table is also 0. And we're going to add it to our other reactant, which is 2 times our water, making sure obviously the right state there, minus 286 kilojoules per mole. A question on the setup there. All right, so doing that, that's going to give me 2 minus 470, basically minus 2 times negative 286. Going to give me a delta H for this, which is minus 368 kilojoules. And once again, here we see a negative value, which means that it's exothermic. And by the way, as you can see here, when you go to these tables for delta H, especially anything that's in this natural state, like H2 and Na, that's not combined with anything else by itself, just naturally how it comes, will always have a value of 0 for delta H. So there'll always be 0 for those guys. Any questions on any of those things?